All right, this is the video on an infinite series, chapter 8.7, page 5 of your notes. We'll get going. The warm-up, maybe pause the video after I explain this and see if you can figure this out. What happens if you start to add up an infinite number of numbers? So you have 1/2 plus a fourth plus an eighth plus a 16th. Think for a second if I kept this pattern going, plus 1 over 32 plus 1 over 64, and I kept that pattern going forever and ever and ever, and then found the sum. See if you can figure out what would the sum be if I added up all of those fractions. Well, I'm not going to answer the question right away. We'll get to it with a little picture down here in the box in just a second. But question number one, what's an infinite series? Well, the word series, if you remember from a couple of days ago, the word series means a sum. So an infinite series would be a sum of an infinite number of numbers. Which right away kind of throws up a warning for me. I'm thinking, okay, can you really add up an infinite number of numbers? Isn't that impossible? I mean, if you keep adding them, isn't the sum just going to keep getting bigger and bigger? Well, the answer to that question, so the question was, can you really add up an infinite number of numbers? The answer I have to that is kind of, or sort of. Sort of, if you think of it this way, your sum will approach a number. Will approach a number. So that word approach is the same word that we use when talking about limits. So you're not going to get an actual number. It's never really going to be, you're never going to arrive at an actual number, but we're going to get really, really, really close to it. So we're going to use the idea of limits to figure out what is that sum, when we start adding, what is that sum that we're getting closer and closer and closer to. All right, think of the warm-up. A good way to model it with the pictures, let's just start shading in. It says, let's say I have half of a box. So I have half of a box right here. We're kind of estimating a little bit there. And I shade in half a box. All right, now I take to that, and now I'm thinking in relationship to the entire box, not just what's left of the entire box. The next thing says, now add a fourth of a box. So a fourth of a box would be one of these guys here. Now shade in an eighth of a box. Well, hopefully it's clear if I cut this in half, I've got an eighth, so I start shading that in. Now shade in a 16th of the entire box. Well, that would be this right here. Now shade in 1/32nd of the entire box. And I think you're getting the idea, 1/64th. Every time if you cut it in half and shade, cut it in half and shade, the question is, am I ever going to shade in the entire box? And the answer is no. You're never going to get everything shaded in. But what's going to happen is what's left is so small that eventually we're just going to say, you want to know what? It's not all shaded in, but it's getting real close to 1. So we're going to say that the sum is 1. So what will happen is the sum will approach a number each time. Well, there's some rules. First of all, your sequence must converge. Your sequence must converge. So it means it has to have a limit. It has to actually approach an actual number. And if you look at the one that we used up on top, this one does converge. Each term that I write down is getting closer and closer and closer to 0. Well, right away that means it can't be arithmetic because arithmetic sequences never converge. They just keep adding and going up or subtracting and going down, so those don't converge. So right away we know that it has to be geometric. Has to be a geometric sequence or geometric series that we're adding up. And even that, it's got to be a specific kind. If it's going to converge, it means that our R value, that number that we're multiplying by over and over again, has to be a decimal. So it has to be in this range right here. Our R value has to be between -1 and 1. So we're multiplying by a decimal over and over and over again so that the value is getting smaller and smaller and smaller. And actually, that's the next question right here for letter C. How do I know if the series converges? You look at your R value, and maybe that should have gone there, is that our R value will be a number that is less than 1 but bigger than -1, something like that. So what's the formula? How can I add up an infinite series? Well, let's think about a finite series. The one that we talked about yesterday says if you want to find the sum of a geometric sequence, you're going to go like this. You're going to take the first term from your sequence, and you're going to have 1 minus r to the n over 1 minus r, like that. This is if the series is finite. So you will know how many terms are in the series. Well, let's think for a second. Now we're just talking about infinite series. So in an infinite series, what's going to happen is we'll have g sub 1. We'll have 1 minus r. And remember, n stands for how many terms, but this goes on and on forever. So actually we're going to have infinity, an infinite number of terms like that, over 1 minus r. At first, now that made it a little bit harder to think about. But let's think about this. The rule that we said is that this r value has to be a decimal, has to be less than 1, and we're going to raise it to a really, 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 really big power. So let's think about what happens when you take a decimal and raise it to a really big power. Well, if you can't think of that on your own, let's just try it. Let's take a decimal by like 0.5, and I'll raise it to a power like power, I don't know, 1. You get 0.5. Take 0.5 and raise it to power 2. Oh, you can see, look, it cut in half. It's getting smaller. 0.5 power 10. Ooh, e negative 4 means slide that decimal places, so this is actually 0.00097, and hopefully it's clear that the bigger the exponent that I put in here, the smaller and smaller and smaller this decimal is getting, or it's getting closer and closer and closer to 0. So if I wanted to figure out what this is going to be, when I do a decimal to a power of infinity, this piece of it gets very, 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 very small and eventually becomes so close to 0 that we can just call it 0. So its limit is 0. So our formula then becomes this. G1 times 1 minus 0 is just 1 over 1 minus r, like that. This formula will work, or sometimes, if you're thinking about how this works, sometimes they take the G1 and they just put it on top, because this is G1 over 1, so another formula you'll often see is G1 over 1 minus r. Both of these formulas are very common formulas. Okay, well, let's give it a try. I'll try one, then you can try one. Here's a series. So I'll give you the first 4 terms. Dot, dot, dot means that it goes on forever and ever and ever, and I want to find out what this infinite sum is. Well, it's pretty easy just using the formula. If I look at this, the first thing we want to do is figure out what the r value is. If I look at the top is the same every time, so that suggests to me that it's times 1 times 1 times 1, and the bottom looks like it's times 3 times 3 times 3, like that. So I have an r value of 1/3. If I want to find the infinite sum now, I can just go to my formula. Say G1 goes on top, so 5/3 goes on top. On bottom is going to be 1, I'm looking at this formula here, 1 minus my r value, 1 minus 1/3, like this, or it's going to be 5/3 divided by 2/3, like that. I can either do this in my head or go to my calculator. Either one is fine. If I do this in my head, I have 5/3 multiplied by the reciprocal, which would be 3 over 2, cancel, cancel, so we're going to get 2.5. So if I were to take these fractions and add them up forever and ever and ever, I'm going to be getting closer and closer and closer to the number 2.5. Something that sometimes comes up is the word partial sum. A partial sum is, well, the infinite sum is when you add them up forever and ever. A partial sum would be just pick a few of them and add them up. So if I ask you to find the 4th partial sum, what that means is you would just take the first 4 terms and add them up. In order to do that, I mean, I can do it, or all you would do is just use the formula that we used in the past right here, where you would plug in r would be 1/3, and the number of terms would be 4, so you could just add that up. So a partial sum means you just pick the first however many terms they say and do it. All right, pause the video and see if you can do number 2 and 3, and then we'll talk. The first thing that you want to do is figure out what your r value is. So if I do this, maybe it's clear what the r value is between your. If you're ever stuck, just take a term and divide by the one in front of it. So I can go 160 and divide by 640 and get 0.25. So I can figure out that the r value is going to be 1/4, like that. If I want to figure out the infinite sum now. The first term goes on top, which is 640. On bottom is going to be 1 minus 1/4, like that. So this is going to be 640 divided by, if I subtract those, 0.75. I think my calculator can handle this just fine. 640 divided by 0.75, and I should get 853.3 repeating. So the infinite sum would be getting closer and closer and closer to this number right here. If you want to find a partial sum, all you would do is just take these four numbers, add them up. If I asked you to find a fourth partial sum. If I said find a third partial sum, it would just be the first three numbers like that. All right, the bottom one, at first you might think, well, okay, maybe the pattern is times 5, but if you look at it, it's actually plus 4, plus 4, plus 4. This one's arithmetic. Ones that are arithmetic do not converge. If they don't converge, you cannot take an infinite sum, so we say DNE. The sum does not exist. Those numbers just keep getting bigger and bigger and bigger. The last quick topic we're going to talk about, we don't need to do all these examples, but something that kind of weaves into this is how do you find a fraction to represent that decimal? So here's what we do. You take the decimal. If you have a repeating decimal, and you just call it x. So we're going to call that x. Then we're going to multiply by a power of 10 to move this decimal place over, and I'm going to move it over one spot. So watch what happens. I'm going to multiply, so let's pull this over here. I'm going to say x is equal to 0.2 repeating, like that. And if I multiply this side by 10, the decimal place slides one place. So if I go times 10, I get 2.2 repeating. And I can't just multiply one side by 10, I also have to multiply the other side by 10, so I get 10x over there. All right, now we're going to do kind of a weird thing. We're going to take two lines and we're going to subtract them. So if I go this number minus that number, so 10x minus x is 9x. And if I go 2.2 repeating minus 0.2, well, look at that. When you do this little process, the reason that we did it is when you subtract them, your repeated decimal goes away. 2.2 repeating minus 0.2 repeating is actually going to be equal to 2. Now I can solve that. Divide by 9, and x is going to be equal to 2/9. Maybe you recognize that decimal anyways, like that. So 0.2 repeating is going to be 2/9. All right, let's try another one. So this one, I have 0.45 is equal to x. We're going to call it x. Now here's something I didn't say before, but it's coming up now. We're going to multiply by a power of 10 however many places we need to slide this decimal to get until it's done repeating. So for example, if I slide it 2 places, then I'm going to have 4, 5, 4, 5, 4, 5 behind that. So this time, instead of multiplying by 10, I'm actually going to multiply by 100. So times 100 gives me 45.45 repeating. So I've got the same repeating decimal right here. Times 100 makes 100x, like that. And now I can do that subtraction again. Do subtraction, I get 99x. Do subtraction, get 45, like so. Divide by 99, and you get 45 over 99. And you've got your fraction. It looks like it can be simplified. Divide by 9 and get 5. Divide by 9 and get 11. So this one is actually 5/11ths when you simplify it. All right, if you get it, try a couple. You don't need to do them all. Try 3 and 4. If you don't, I'll do them right now. If you get them, then pause it and try it. Otherwise, I'll do it right now. I need to slide this one 3 places to get to the repeating part. So I'm going to go x is equal to 0.123 repeating. 3 places means 1,000. So I have 1,000x is equal to 123.123 repeating. Subtract, I get 999x is equal to 123. And now just divide, I get 123 over 999. I'll see if that reduces 123 divided by 999. See if my calculator can do that. I'll hit math and frac. Yep, looks like we have 41 over 333 is going to be your final answer. We'll do one more and call it good. Let's see. For this one, I'm going to call it x is going to be equal to 0.078. The 78 is the repeating part. So I need to go 1, 2, 3, multiply by 1,000 x to get to 78.78 repeating, like that. Actually, I'm going to change that. I want to get to the repeating part, so I'm going to multiply this one by 10 and put the decimal right here instead. The reason I did that is because now the repeating parts line up so that when I subtract them, they'll go away.